All right, welcome back. So we talked about the return to scale, and we're going to talk about isoquant today. So what is isoquant? So iso means the same, and quants of course means quantity, right? So isoquant means the same quantity. So in other words, isoquant curve is the set of all the possible combination of inputs if used efficiently to allow the production of the same given level output. So we looked at something similar, in fact, mathematically identical one. So that is indifference curve. So let's say so we have utility function of x1 and x2, and you fix the utility level at u0. So this was representing an indifference curve, right? So then it's the same thing here. So let's say f of lk. So here I'm using I1 and I2. So here, so let's say f of I1 and I2 um, is a production function. And I'm fixing at a certain level of Q0. And this will describe all the possible combination of I1 and I2 that can give you Q0 as an output, right? So this will define this implicit function will define an isoquant curve. Okay, so mathematically they are exactly the same thing. Just so you were just using different name for the functions and the inputs or functions and the arguments. So I don't have to explain anything here. So by the same reason that indifference curve had a negative slope, isoquant will have a negative slope. So indifference. So for the utility function, if both of them are goods, then indifference curve had a negative slope, right? So here, if both of the input factors is helping the production, if they are helping the production, then the isoquant curve have a negative slope by exactly the same reason. And isoquant farther away from the origin correspond to higher level of output. So as in the set of indifference curves, the higher indifference curve is the one that's being farther away from the origin. Um, and isoquant curve do not cross each other, like the indifference curve do not cross each other. Exactly the same reason. Okay, so if you study the consumer theory well, there is nothing to study here, just a different name. All right, so the economies of scale. So that's a different story because in the utility function in the consumer theory, the name utility level didn't mean anything much, right? So utility level 12 and 8, it doesn't really give me much information other than that 12 is larger than 8. Even the difference, like 12 is larger than 8 by 4, this by 4 doesn't carry any meaning in the consumer theory, right? But however, in the production theory, these numbers are important, right? Producing 12 units, producing 8 units, and producing 4 more units than 8 units, those are carry or very physical meanings, right? So so that's why we introduced this um, so we could talk about the economies of scale in the production theory, right? And these pictures are representing one of the three cases. So if you look at the first graph, you increase the first and the second input factors by 50%, right? And the output has doubled. So in other words, if I had double the input factors, the output will be more than the double. So in that sense, this is an increasing return to scale. You double the input factors, the output increases more than the double. And this is decreasing return to scale. Here, I increased the input factors by 150% for both of them, and output has doubled, right? So in other words, if I had doubled the input factors, the output will be less than the double. So in other words, that's the decrease in return to scale. So constant to return to scale is very straightforward. So what is the slope of an indifference curve? That's the marginal rate of substitution, right? So in the production theory, we call it marginal rate of technological substitution. So this is a typo. This should be technological substitution, I think, right? So how did I compute that? So this is a utility function. So that means du is ux times dx plus uy times dy, right? So if you increase x by 1 unit, then utility goes up by this much, and this is how much you're going to change your x. The same thing for y, and when we do the calculus, we're treating everything as if they're linear. So I'm just going to sum them up simply, treating them as linear functions. So this will be the total differentiation. And since I'm talking about the slope of an indifference curve, so I'm looking at the one specific indifference curve. So utility will not change on that indifference curve. So rearranging, this will be dy equal to minus ux over uy times dx. So when x increases by 1 unit, y will decreases by ux over uy. So that's called marginal rate of substitution. So when you decrease x by 1 unit, the y has to goes up by has to go up by MRS. So the same thing here. So I'm just relabeling everything, okay? So instead of U, I'm writing Q is f of, let's say, L comma K. That's it. So 0 is dq should be fl times dl plus fk times dk, right? So all the intuitions are exactly the same as in the consumer theory, so I don't have to explain it anything at all. It's all the same thing, okay? So if you study the consumer theory well enough, there's really nothing more to say about it. So this is just this is what I just explained. We can also actually compute the decreasing margin rate of technological substitution. I mean, we could have done it in the consumer theory, this one too, but I don't know why I didn't do it. Maybe I should do it next year. But anyway, so next thing is indifference curve. The isoquantic curve looks like that or looks like that. Okay, so to determine that, we need to determine the sign of that. So in other words, what happens to the slope when I change L, right? So here, the slope is becoming flatter, but the slope is a negative number, right? So let's say it's -3 or -1. No, sorry. No, MRTS is actually the positive, looking at the positive number, right? So yeah. Yeah. Oh, yeah. Yeah, but I actually computed the minus f over. So actually, this is minus MRTS, okay? So many textbook defines MRTS this way, but certain textbook defines this way, okay? But I'm gonna take this convention in the whole course, okay? I think this is the most more popular convention. So anyway, so I should write down minus here. So I need to, so -3 becoming -1, that's increase, right? So if this is the case, then the isoquant curve will convex. So what's the condition for this to be positive? What's the condition for this to be positive? So here, so let's say this is a G of LK. So so this is looking at the change of L and K and the slope at the same time, right? So I'm looking at it on a given in isoquant curve, right? So in other words, when you change L, K is going to change automatically because to be on the same isoquant curve, K has to change as well. Because otherwise, if you change L only, then you're going to jump to a new indifference curve, right? So here, just using a simple chain rule, this is going to be this. So here, by looking at the first variable, this is looking at the first effect. And when you increase L by 1 unit, K will change by this much. And this is measures when K changes by 1 unit, how much G changes, right? So you need to multiply them to make the whole change, right? And we're doing the calculus, so we're gonna treat everything as if it's linear. So I'm just simply gonna add them up. So this is it. So if you do the compute it, eventually you're gonna get this one. And here you have minus sign here, and this is these are negative typically, right? Because these are because the marginal productivity in labor goes down, diminishing marginal productivity in labor and diminishing marginal productivity capital. So that's it. So that's why these are negative numbers, and these are positive numbers, and these are also positive, right? Because the marginal productivities are all positive typically. So so this is also positive. This is also positive. So here, if FLK, which is the same as FKL for most of the functions economists use, if this is the case, then the whole thing is positive. Okay, so we conclude that the isoquant curve look like that. Okay, so even if they are negative but small, if the absolute magnitude is small, then we still get the positive, and it's gonna still look like that, right? Because these two terms will dominate these two terms when the effect is small, right? So anyway, so what's the meaning of this FLK? So FLK is round over round L times FK. Not times. Yeah, I should say. Yeah, I should not say times. I just meant round round L FK. So what does it mean? So what does it mean this is being positive? This means that if you increase labor by 1 unit, marginal productivity in capital goes up. So in other words, having more of the labor helps the capital. So it makes the usefulness of the capital higher. So in that sense, labor is helping the capital. And FKL, which happens to be the same as FLK, is the opposite but the same story. So what it means is that when you increase capital by 1 unit, FL goes up. So in other words, the marginal productivity goes up. So in other words, having more of the capital makes the usefulness of the labor higher. So in that sense, they're complementary. Okay. And Of course, if they're negative, that means they're substitutable. So making more of the labor makes the usefulness of the capital smaller. So that's when the two input factors are substitutable. But anyway, if they're substitutable a little bit, that's okay. But if they're substitutable too much, then we can have this shape of isoquant curve. All right, elasticity of substitution. We did exactly the same thing in the consumer theory, so I'm not going to do it again. This is exactly the same concept with just a different labeling, okay? So we consider the linear utility function, Kopdal's production utility function, Leontief utility function, CS utility function. So we can do all these things again, which I'll of course not do that because we already did it, right? Just doing it in a different name. But we didn't talk about the CRS, DRS, and IRS because that kind of concept does do not mean anything in the consumer theory. But here in the producer theory, this means something. So let's think about the linear function. So this will be output Q when you have X and Y input. So now let's say you increase X and Y by M, multiplied by M, where M is larger than 1. That means the output will be A over mx plus B2 times my. That is M times ax plus by is M times q, right? So this is a constant to return to scale. If you multiply input factors by m, the output will be previous output multiplied by m. Okay, so this is the CRS. So linear production function is a CRS function. Now let's think about the Kopdal's utility production function. Okay, so this is the output Q when you have input L and K. Now I multiply M to L and K, then the output is ML alpha MK to the power of beta, so that's going to be M2 alpha plus beta times AA alpha K2 beta. So in other words, M2 alpha plus beta times Q. So if M2 alpha plus beta is M, then that's a CRS. And M times M2 alpha plus beta is larger than M, that's IRS. And if this is the case, that's DRS. Okay, so when it's gonna be? So of course, M is always larger than 1, so that's when alpha plus beta is 1, that's when alpha plus beta is larger than 1, and that's when alpha plus beta is a smaller than 1. Okay, so that's going to be the, so the Kopdal's function could be CRS, IRS, or DRS, depending on the value of the alpha plus beta. Okay, so Leontief. So I'll give you two examples. So let's say Q is a minimum of L comma 2 times K. Okay, so that's the input factor of L and K. So if I multiply by M, and of course M is larger than 1 as usual, then the output will be minimum of ML comma 2 times MK. That's the same as M times minimum of L and 2K, so that's M times Q. So that's a CRS. Okay, but it doesn't have to be CRS all the time. So for example, so this is the Leontief function. This is a perfectly valid Leontief function. And if I increase the L and K by multiplying m, the output will be square root of ml, 2 times square root of mk, that will be square root of m times minimum square root of L, square root of 2 times square root of K. So that's the square root of M times Q. So that will be smaller than M times Q. So this is a decreasing return to scale. Okay. So you can do the similar thing with the CES. So you can check it yourself. All right. So technological progress. So we didn't have to consider this kind of thing in the consumer theory because typically we are fixing the utility function, right? So we never think about the change of the utility. I mean, theoretically we can think about that, but from the data, it's going to be, but applying data to that theory will be very difficult because when you see some change, it wouldn't be easy to identify where the change comes from. The change could be coming from the change of the environment, like prices and income, or it could be coming from the change of the utility function. And identifying where it comes from will be very, very difficult. So first, it's going to be difficult. And second, we somehow believe that the utility function doesn't change that much over a short period of time. Because otherwise, like, I don't know, size, I mean, even if they change, we're trying to find out some consistent uh, um, how do I say, consistent results from the consumer optimization. So even if it changes, I mean the wisdom we're gonna get from the theory will not really change much. But anyway, all right. So this is an example of the technological progress. As you see, an isoquant curve is changing to a different isoquant curve. So both of them are Q equal to 10, right? So this is the pre-innovation isoquant curve. And this is a post-innovation isoquant curve, okay? So as you see here, using less of the input factors, you can produce the same amount. So, so that's called technological progress. And the technological progress can be labor saving, or it could be capital saving, okay? So we didn't fully specify what the producers objective functions to maximize yet, but we'll see that eventually. We'll see some kind of a tangent line to this isoquant curve, right? Like in the consumer theory, your optimal decision is made where the budget line is tangent to the indifference curve, right? So we're gonna see something similar, not exactly the same, but something similar. And there, the slope of the budget line is represented by the price ratio of the two goods, right? So here we're talking about the labor and capital. So the price ratio will be with respect to price of labor, which is wage, price of labor, and R is the price of capital, which is rent. Okay. So anyway, so in this environment, suppose there was a technological progress so that the isoquant curve has moved. Okay, then what's gonna happen? Um, Your optimal decision will be somewhere here if you insist on producing 100 units again, right? I mean, of course, when things have changed, you may want to revise your production scheme of producing 100 units, right? So you might want to produce more, or you might want to produce less. But suppose you want to produce 100 units, the same amount again, okay? And the price of labor and price of capital didn't change, only the production function has changed because of technological progress. Then this will be your optimal, okay? So as you see here, the ratio of K of L went up. So in other words, you're using more fraction, more of the capital than labor, relatively speaking, of course, because anyway, both of the labor and capital usage has decreased because of this technological progress, but the ratio has changed. So you're using less of labor compared to capital than before, right? So in that sense, in that sense, this is a labor saving technological progress. In other words, capital can somehow substitute a little bit of the labor. Okay, so this is called labor saving technological progress. And if the slope here is the same as before here, then the slope at the um, original ray originating from the origin will be flatter, right? So that's why we have this picture. So the MRTS slope of isoquantic curve becomes flatter on this line. So that's labor saving technological progress. So capital saving technological progress will be the opposite picture, right? So let's say initially your optimal decision was something here, right? And your optimal decision was here, and this never works somehow. And then this would be your new optimal decision, right? But if you look at it along the original capital and labor input ratio, you can see that the slope is steeper here, right? So this is how so the MRTS gets larger along these previous labor and capital input ratio. Okay, so this will be capital saving technological progress, the opposite of the previous picture. All right, so total cost of production, that will be how much you use the input factors times the price of the input factors and add them up. Okay, so we looked at something similar, right? So in the consumer theory, this was the expenditure on good X and good Y. So this is the expenditure on the input factors, right? So it's the same thing. Of course, more generally, the amount paid per unit can change depending on the quantity used. So like in the consumer theory, we could generalize it so that Px becomes a function of X and Py becomes a function of Y, right? But we're going to use that kind of form rarely. We'll probably stick with this one more often. So unless mentioned otherwise, we typically mean this as the cost. All right.